So what is that you need here? That doesn't work, everything?
Sorry? Yeah, it works.
Okay, so you can put it into your pocket.
Yeah. Can you hear me well? Is it okay?
Yeah.
Yeah,
Yeah.
but the machine you can put it in. Well, try to see if it moves.
This is to go forward and then
Does it work? Yeah, so go back.
Press. Yeah,
Okay.
and there is the
No, pointer will not
the
work.
laser.
pointer? Okay.
I
That's
can
okay.
ask. Also, they have.
No, it's not.
So we will continue this morning section with Josef Svoboda to tell us about Q-series invariants and abelian covers. We are standing 5 minutes late, so until 12:05. Okay.
Okay.
Did it work?
Yeah, 1 minute to go.
I don't know.
Okay. Yeah. So this talk is about some topological aspects of algebraic geometry. So I just want to, I just want to move the lights. Maybe I can do it like this. Yeah. So first I want to say that algebraic geometry was always very important, like a driving force for topology, especially in the beginning and mid 20th century, but also later. So, for example, on the homology groups and cohomology groups of algebraic varieties, there are Hodge structures. So if you want to study geometry, you first need to know what is the topology of the algebraic variety. Also, algebraic varieties have interesting fundamental groups. Another topic are algebraic surfaces, and they play a very important role in the 4-dimensional topology because they provide a whole bunch of examples, very non-trivial examples. And another topic which connects geometry with topology are surface singularities, because they naturally induce 3 manifolds. So this will be the topic of the day, the relation of singularities and 3 manifolds. So the 3 manifolds which come from singularities they are sometimes called links of singularities, which shouldn't be confused with links in R3, like bunch of knots. It's a different, completely different notion. Unfortunately, it's called the same. So they show interesting properties of invariants. So they are very useful. If you have a new invariant, you can look at these manifolds and compute. And they are simple enough. Usually they are simple enough to compute things. So they are very useful in this way. So the reason why they are kind of simple is that they you can always decompose a 3 manifold into pieces with some Thurston geometry, and the most interesting one is the hyperbolic one, but there are no hyperbolic pieces for links of singularities. So in that sense, they are very, very special, very non because the generic one are the hyperbolic. But as I said, the big advantage of these 3 manifolds is that the invariants can be actually computed in a combinatorial way. So very important example is Hegardt-Fuller homology of Oswald and Szabó. And this one has a combinatorial version for these kind of manifolds, which goes by name lattice cohomology. And it was developed by Nemeti and used for computations of Hegardt-Fuller. So it's called lattice cohomology because it's defined using the natural lattice which is assigned to this tree manifold, and I will talk about this lattice later. At the same time, they are very interesting because some invariants were first defined for this class of manifolds, and then it took like many years to extend them to a general tree manifold. So this is the power of the combinatorics. So for example, there was an invariant mu bar which was defined independently by Siebermann and Neumann. And this invariant is defined for the links, and it took 33 years to extend it by work of Manolescu, who defined this invariant beta using Seiberg-Witten theory. And today I will talk about a different kind of invariant, much more recent, which is this Z hat BQ invariant. So this invariant was also first defined for links of singularities. So it goes kind of in a similar way. And it is a big problem to extend it for general tree manifolds. Yeah, and the last point why it is interesting to look at these kind of manifolds is that the invariants usually come in pairs. So there is usually an invariant of a singularity, an invariant of three manifold, and they share properties. So for example, for Hegardt-Fuller, there is a new, very recent invariant which detects the analytic structure of the singularity. And this is this analytic lattice cohomology of Nemeti. It is a categorification of geometric genus of the singularity. So you can have a fixed tree manifold, and you can have lots of different singularities which have the same topology. So the discrete invariants like geometric genus can jump in this moduli space, and this analytic lattice cohomology detects this. Okay, so it is also interesting from the point of algebraic geometry because you can look at the topological invariants and try to cook up some analogical invariants of singularities. So now I want to talk about quantum invariants. So quantum invariants are invariants of three manifolds which were they are called quantum because they are related to quantum groups and representations of quantum groups. So the famous Jones polynomial is a quantum invariant, and Jones polynomial is defined for links. Now I mean links and knots in R3. And this was the first important invariant, and then there was a lot of progress. So one is the categorification of Homanov. So there is this Homanov homology, and then also there is this famous extension by first Witten using Chern-Simon's gauge theory, and then made like mathematically rigorous by Reshetikhin and Turaev in 1991. So those are the Witten, Reshetikhin, Turaev invariants and Homanov homology, two different extensions. So Homanov homology famously doesn't extend to three manifolds. There are some physics proposals by Witten, but we still don't have the definition. And these new invariants Z hat defined by Gukov Putrov Pei-Vafa are aiming to fill this gap. So they are aimed to be they should lead to the categorification and to extension to of Hovanov homology, because Hovanov homology is like SU2 invariant, so there is a gauge group, and these also have a dependence on gauge group and should have this role. Yeah, so now I want you to kind of remember from this talk that there are three important problems here. One is that, as I said, these invariants are so far defined for these links of singularity. So this was the first class, and now the big question is how to extend them to general free manifold. So maybe there is no extension, but there are physics expectations which tell us that there should be an invariant of a completely general free manifold. And there is a lot of ongoing work on this started by Gukov and Manolescu, and then there has been a lot of development by Park, student of Gukov and others. So the idea is that you try to do dense surgery and find some formulas by how this invariant should behave under dense surgery. But it's a complicated problem. The second problem is categorification, of course. So we want to have some vector spaces, and there is a physics proposal. So there should be some 3D supersymmetric quantum field theory, such that the Hilbert spaces should categorify this series. And this second problem is related to the third problem, and that's the question about actually getting some interesting topology out of this invariant. So there is a hope that actually once we categorify these invariants, they could lead to some interesting invariants of four manifolds. And in this sense, we are getting back to singularities, because singularities are basically four manifolds, right? I mean, you can resolve the singularity, you get a four manifold with the boundary being the link. So our work is kind of related to the problem 3. Yeah. So now I want to get to our results. So we have a paper preprint with Sergei Gukov and Ludmila Khazarkov. And we don't aim to categorify or extend to general free manifolds. We rather look at the series and try to see some properties, and we are motivated by singularity theory. So we looked at various papers in singularity theory and wanted to see if the techniques can be applied to Z-hat invariant. So the first result is that there is a nice, very simple formula for Seifert manifolds, which are links of quasi-homogeneous singularities. So we had in previous talks we had quasi-homogeneous singularities. So their links are Seifert manifolds, and we can simplify a lot the formula for this invariant in this case. And this has some nice applications. For example, it was observed that this invariant often vanishes for some so there's this label B, which I will talk about later. So for some choices of B, this invariant completely vanishes. And this is now much better understood with the formula. And the second result relates to this invariant to the abelian coverings of the free manifold. So it's a technical result, but it implies that we can find two very different manifolds, but they have something common. And the thing which is common is the universal abelian covering. So they are basically quotients by different finite groups of the same manifold. And we found and proved that a certain combination of these Z-hat invariants, it's actually just the sum over the labels B, coincides in this case, up to some scaling. So here is an example of this invariant. So you can see that it is a Q series. It goes to infinity. There are integral exponents and coefficients, except from some powers of 2 and some of 3 factor. So this is why people hope that there is a categorification because of this integrality. Okay. So this was general introduction and motivation, and now I want to get a little bit more technical. So let's start with the singularity. If we have a complex dimension n, then there is so it's an isolated singularity. So if you look at the neighborhood, it looks like a cone over something, and the something is a smooth n-1 manifold. So it's important that the isolated singularity is isolated, otherwise it wouldn't be a smooth manifold. So in dimension 1, we have algebraic curves, and the links are just the usual links. So something embedded, some circles embedded in R3. So maybe that's why these things are called by the same name. So we take this equation x squared plus y cubed, and we intersect with the unit sphere, and what we get is the trefoil knot. So and they're called algebraic knots because they're coming from algebraic equations. So there has been a lot of study about this, but this is not really what we want to do. There is also dimension 3 and more, and funny things can happen. So topologically, the link can be even a sphere, so the topology can be completely trivial, and this leads to these famous exotic spheres of Milnor. And so Milnor had a different construction, but then Brieskorn found like explicit equations which gives these exotic smooth structures. Yeah, and so what are we interested in the most is the dimension, complex dimension 2, so complex surfaces, because then we get always a non-trivial 3 manifold. So unless the singularity there is no singularity. So this is the case when the topology actually tells us a lot about the analytic structure. Yeah, so in the dimension 3, it can be nothing. Here it is something. So yeah, so let's take a germ of normal isolated surface singularity. We embed it into some C to the n and intersect with a little unit sphere. We get a 3 manifold Y, which is the link of singularity, and it is a plumbed manifold. So here is some kind of picture. So you can resolve the singularity, and then you have the exceptional divisor, which looks about a bunch of spheres, and it gets mapped to the singular point. And one way how to look at this link is that it's a boundary of the tubular neighborhood of the exceptional divisor. Yeah. So you can look at it from the point of the singular resolution of the singularity. You can also look at it as a boundary of the single surface intersected with a sphere. Yeah, so I need to say a little bit about this plumbing. So plumbing is a topological construction when you start with some surfaces, two-dimensional real surfaces, and you have circle bundles over them, and then you can glue them by this funny way. So you take a circle in the fiber and circle on the surface, and then the product is a torus, and you can glue them in this fashion that you glue the circle in the boundary of the surface with the fiber, and the other way. And yeah, so you use this 0, 1, 1, 0 matrix, and this gives you some interesting 3 manifolds, and those are exactly the 3 manifolds which come from the links of singularities. Yeah, so they are all glued from surfaces in this way, and we record them by drawing a finite graph where we put a dot for each sphere, and we put an arrow whenever we glue. So we get all these manifolds. Yeah, and finally we put E1, E2 for the Euler numbers of the possibly non-trivial circle bundles over the spheres. Yeah. So the upshot is that these kind of manifolds can be all encoded in a finite graph with some labels on vertices. So that's why we can do combinatorics. Yeah. So here's an example. So if we take x squared plus y cubed plus e to 7, it's a nice algebraic equation. We can intersect with the 5 sphere in C3, and we get a so-called Brieskorn sphere sigma 237. It's not so important, but what is important that here is the plumbing graph. So it can be glued by four circle bundles and spheres, and with these Euler numbers. And you can also encode it into the plumbing matrix, which is just a matrix which has these Euler numbers, these labels on diagonal, and then 0 or 1 if the two vertices are connected by an edge or they are not. Okay, so this is what we want to play with these matrices or these graphs. Any questions? Okay, so here is the famous paper of Neumann, where he actually developed some kind of calculus based on Kirby calculus for knots and links. But this one is much simpler because we have just graphs. There are no complicated knots. And he showed that there is a certain set of moves. So when you change the graph according to these moves, the three manifold doesn't change. Yeah, so it's important to have in mind that this graph determines a three manifold, but it's not like that the three manifold determines a graph. It's a class of graphs under some moves. So the graph is really the four manifold we choose. Like kind of it's like the resolution of singularity which we choose, and there are lots of resolutions. So whenever we have an invariant, whenever we want to construct an invariant of plumbed three manifold, we need to make something out of the graph, and then we need to make sure that it is invariant under these moves. So here is an example of the move which preserves the three manifold. Yeah. So any invariant should give us the same number or same polynomial under such a move. Yeah. And as I said, the plumbing graph corresponds to the resolution of singularity. So the exceptional divisors, how their self-intersection are the Euler numbers and how they intersect with each other. And there is this famous result of Mumford from 61, which says that if we have a resolution of normal surface singularity, then the matrix must be negative definite. So in particular, this means that there is this important condition that the plumbing matrix of a link of a singularity also needs to be negative definite because it's the same matrix. Yeah. And I want to emphasize that this is very important condition, and it's crucial in the definition of the z-hat invariant. Because if you don't have this negative definite condition, then you don't have the convergence of these Q series. Okay, so that's another obstacle which we need to overcome if we want to generalize this three manifold invariant to more general three manifolds. Okay, so here is the formula. So this is the important and a little bit scary formula. So I will try to explain it in a great detail. So the input is the negative definite plumbing matrix M, or the plumbing graph. And there is an additional little piece of data, and that's the spin C structure B. But you don't have to worry that much about it. It is so you can think about it as there is this plumbing matrix M, and this gives us a lattice because we take z to the n, and we act by this matrix, gives us some image which is again embedded in z to the n. And sorry, I moved it. And B is just some vector in this lattice. Yeah. So this is the lattice in lattice cohomology. So yeah. So there is a sum. So there is this dependence on B, and then there is dependence on variable Q. So there is some prefactor Q to delta. Then there is some scary integral. But what this really means is just that we take a constant term in each of the dummy variables ZV. So we have a variable for each vertex of the graph. And then there is this rational function ZV minus 1 over ZV to some power depending on the degree of the vertex. And finally, there is this big theta function. So there is quadratic term, Q2 something quadratic, depending on vector in the lattice, and ZV to the LV. So basically, what it means in a practical way, if you want to compute or if you want to just like see what it is. So there is the important thing. The first important thing is this rational function. And it's a very funny rational function because usually what you see in algebra is exactly this function, except that there is degree minus 2 and not 2 minus degree. Yeah. So when you have degree minus 2, it's the usual Poincare series of some graded ring. But here it's kind of inverted. It's 1 over Poincare series. And then the second important ingredient is this coupling with the theta function via this integral. And what this really means is just that we expand this rational function as an infinite series, a Taylor expansion, and then to each of these terms we substitute for z to the L just this quadratic Q2 L squared with this and inverse. So it really is just some big substitution. You expand everything in as you have as many variables as the vertices of the graph. And then for each of these monomials, you substitute using this quadratic form M inverse. And finally, you multiply by some prefactor, just some power of Q, because otherwise it won't be invariant under the Kirby moves. And it's kind of a miracle that in the end you get something which is invariant under the moves. Any questions about this definition? Okay, so in the end we get a series, and it converges in the unit circle because of the negative definite condition on M. Okay, yeah. So Gukov, Putrov Pei, and Vafa found this because by looking at Witten-Reshetic in two-rife invariants, so they are defined in the roots of unity, and they were looking for some natural extension to the whole unit circle for Q, and this formula gives the natural extension. So this invariant extends further the Witten-Reshetic in two-rife invariant to the whole unit circle. Okay, yeah, so this is what I already said. So the last bit of the definition is that there was this little shift in the theta function so we are summing over some shifted lattice. So whenever you have a spin C structure on your three manifold, it gives you some subset of the lattice, and you sum just over this subset, and this gives you additional dependence on a spin C structure. We always assume that our manifold has finite H1, so that we have only finitely many spin C structures. Okay, so here is an example. So if we have x squared plus y cubed plus 1 to 4, it's not really important, it's just some example. We have this plumbing graph, and if we plug this plumbing graph into the formula, we get some nice infinite Q series, which we can study. And there are three spin C structures, and there is this interesting symmetry of the invariant with respect to spin C conjugation. So there are really just two Q series. Okay, so now we are coming to our results. So Seifert manifold is very special class. Seifert manifolds are links of the homogeneous singularities. So, for example, this singularity is homogeneous. Here you can put some weights on x, y, and z so that you can make it homogeneous. So this three manifold has a special structure. It's exactly like in the previous talk, and the special structure is a S1 action. So it is a vibration over some surface, two-dimensional surface, and there are some singular fibers. And we will consider only fibration over S2 over the sphere because we want this condition on a homology to be finite. And then the Seifert manifold can be completely encoded in terms of Seifert invariance, which is a bunch of tuples of numbers, AIs and BIs. And they exactly encode these singular fibers. Yeah, so the A's are like the orders of isotropy. Yeah. And since we are talking about plumbed manifolds, it's useful to have a plumbing description of the Seifert manifold. And this is kind of, I mean, it's kind of ugly in the sense that the graph will be very big, but it's kind of nice in the sense that it's star-shaped. So it is really just one vertex, and then there are many legs, as many as the number of singular fibers. And the labels on the legs are given by continued fractions. So that's why you can get kind of big, because continued fractions can be very long. Yeah, so okay, so you can compute the invariant by taking this huge graph and plugging into the definition, but then you will have really many variables, so it is kind of computationally heavy. So one of the goal of our work was to take this invariant and express it in terms of just the Seifert invariance, which is a very natural thing to do, and it works out. So first, so one of the lessons should be that it's easier to work first with this invariant Z0, which is just the sum of all Z hat over all the spin C structure. So it's like a sum over the whole lattice. And then it's easier to find the formula for this one, and then kind of use the equivariance under the H1. So let's denote big A, the product of all AIs. And we have this Laplace transform kind of substitution. So we take a monomial T to the N, and we send it to Q to N squared over 4A. So this is what makes, this is similar as in the definition of the Z hat, but now we have just one variable instead of as many as the number of vertices. Okay, so here is the theorem. So if Y is Seifert manifold given by this Seifert data, and we assume the usual assumptions like it's negative definite and the H1 is finite, then we take this denote F0, this function, rational function, just in one variable, and the formula says that Z0 of Q to the power of H, so that's just a normalization, is given by a symmetric expansion of this rational function, and then the substitution LA. So we have just function of a single variable, we expand it, and then we substitute to this quadratic power. And somehow it gives the same answer as if we would do this with this huge matrix, which is nice, but it doesn't work like completely, but it works up to a power of Q. So there is this little delta, and this delta is related to Kasson-Walker invariant. So there is, it's not, yes, we have two things. One is a huge series in many variables, and then you do a substitution. The other one is just one variable, you do substitution, and they are almost the same, except from a single power of Q, which is a more well-known invariant. Okay, and what is important to notice is that you can see that there are no B's whatsoever. I mean, actually they are there because they are hidden in two things. They are hidden in the order of H1, and they are also hidden in this delta. But except from that, they are not there. They're not in the function f0. So, and this is related to the fact that we are looking at the z0, the sum over all b's. Oh, sorry. I'm using B for spin C structure and also for the Seifert invariant, so don't get confused by that. We are doing sum over all spin C structures, and we lose the dependence on BI's. From that you can see that actually if you take two Seifert manifolds with the same A's but different B's, this series will be more or less the same, except from the scaling of Q and some refactor of Q. So this leads us to the second result, which is now general. It's not just for Seifert manifolds, but it works for any plumbed negative definite manifold, and it captures this independence on B's. Yeah, so there is also equivariant version. So from the formula for Z0, we can extract formula for all Z hat B's by putting some characters of the H1 into the play. So that's a usual trick, but it took some time because it is more natural to, in this case, it's more natural to think of some slightly modified invariant, which actually depends on element of H1 rather than a spin C structure. And then you can sometimes get the Z hat invariants, but sometimes there is still some tiny discrepancy between this Z hat prime and Z hat. Actually, if you want to compute Z hat, you still need to do a little work because sometimes there are like more spin C structure which have the same Chern class. Yeah, okay, but more or less this gives a formula in terms of just one variable function for all the Z hats. And I want to say that this is analogical in theorems of Nemeti for other invariants like Seiberg-Witten invariants or Hegar-Foer. So we call it reduction theorem because it reduces the number of variables, or it reduces the number of vertices to just one important vertex. Okay, so the question is, what is the analog of this A1, A2, and AK for a general plumbed manifold? Yeah, so we notice that they are more important. These numbers are more important than these. So there is some very funny combinatories developed by Neumann and Wall. So we start with the plumbing graph, and we do the following thing. So we take the same graph, but now we will put some weights not on the vertices but on the edges, and it will be on each side of each edge. So if you look at this one, for example, with the arrow, we look at the part of the plumbing graph which is cut from this edge, and we look at the determinant of the corresponding submatrix, and we record it here. So one is the determinant of the submatrix, the -1, -1, -2, -3 on diagonal. We do this for every single edge, and we call this a maximal splice diagram. So it's a lot of determinants, but that's it, yeah. And now there is a very involved linear algebra theorem, and this says that the maximal splice diagram actually recovers the plumbing graph. So this operation can be inverted. You can get back the plumbing graph from all these determinants. So if you take a plumbing matrix, we denote the algebraic matrix is just the inverse times determinant. And so the way how it works is that we look now at this maximal splice diagram. We take two vertices. So we want to get the entry of the plumbing matrix. So we get two vertices, and we connect them by a path, and we look at the product of all the attached numbers, 2, 2, and 5. We multiply them, and this is the entry of the educate matrix. So one way, so we first do some bunch of determinants, and then we can get back by looking at all the different paths between two different vertices and multiplying the entries around this path. So I think this is a very nice construction. And and now so this is just one way how to, there are two ways how to encode the same data, right? But now once we have this splice diagram, this maximal splice diagram, we can encode just some important information, and that is by we erase the vertices of degree 2, and we erase all the numbers around them. So this is the splice diagram. So that's an important definition for us. So you may notice that we erased this middle vertex here, and we erased the numbers around. And this is exactly what should be the generalization of A1, A2, up, and AN. So if you would have just a star-shaped graph, like we have this 2, 3, 7, you'll see that the 2, 3, 7 are here, and we lost the B1, B2, B3. Okay, so it's a direct generalization of these isotropies of the singular fibers. Yeah, and so here's the second theorem. So if Y is a singularity link, which is a Q homologous sphere, meaning that the H1 is finite, then the series is 0 when we do the same thing. So we scale the variable Q, and we multiply by -6 times the Casson Volcker invariant. Then this series depends only on the splice diagram of Y. Yeah. And this generalizes the independence of Z0 on the BIs. So maybe I can say a little bit about are there any questions about this theorem? So it says that this particle combination of the Z-head invariants can actually be recovered from less data than the full plumbing graph. And maybe I can quickly say something about the proof. So the Z0 is just a sum over the whole lattice of these quadratic terms. So we can we have this rational function, we expand it, and then we look at these quadratic terms. So when we expand it, we can notice because of this 2 minus degree V, that if the degree is 2, we will have just 1, right? There will be no variable ZV for degree 2. So all these vectors in the expansion will have zeros when we have degree 2 vertices. So there will be some plus minus ones for the degree 1 vertices because we have 2 minus 1 is 1, so it's just Z minus 1 over Z. Then there will be a bunch of zeros for the degree 2 vertices. And then there can be any numbers, some other numbers for larger vertices, larger degrees. And also you're getting some combinatorial numbers in front of because you are expanding higher and higher powers of Z, 1 over Z minus 1 over Z. So you have a bunch of vectors like this. And then you plug them into the quadratic form. And basically, this means that the only thing which are non-zero in this exponent are things which come from a pair link, degree 1 vertex, and something of degree 3 and more. Or it can be leaf with itself. So remember that in the plumbing in the splice diagram, we exactly lose. So by this theorem of Neumann, these informations of inverse matrix are recorded in the splice diagram, and we exactly removed the information of degree 2 vertices. But we removed one more thing, and we removed the weight here, like the link with itself. So this is something which is missing when we do this quadratic terms. But luckily, if we do, since we have plus minus 1 here, we will have like plus minus 1 times the algebraic matrix of M times plus minus 1. So these things cancel. And the contribution of relief itself is just sum over these kind of terms algebraic BV for leaves. And this is exactly what appears in the formula for Casson invariant. So this is how we get the Casson invariant, which is here in the exponent. So it's a very lucky thing that there is something which would make problem because it's not in the splice diagram, but it actually contributes just by a uniform power of Q. Okay, so this is about the proof. Any questions? Okay, I have like 10 minutes, right? Or 5? Yeah. So yeah, and so there is this nice corollary about for this theorem, and that says that if we have two manifolds which have the same universal Abelian cover, so I didn't say this, but the splice diagram, the original motivation to even define this notion was to study singularities, and it was to study universal Abelian covers of singularities. So this goes back to Klein, and then it was mainly done by Neumann and Wall. They noticed that if you have a quasi-homogeneous singularity and you look at the universal Abelian cover, then it is actually this nice Briggs-Thorne type of equation where you don't have any mixed terms. So this was very surprising. And then they thought that this is property of quasi-homogeneous singularities, but then they noticed that there are some other, and they found out that the important thing which describes the universal Abelian cover is exactly this splice diagram. So if two manifolds have the same splice diagram, this more or less means that they have the same universal Abelian cover. So if we have two, so the corollary says that if we have two manifolds which are related in a way that they have the same universal Abelian cover, then the series up to these modifications coincide. And here is an example from Neumann and Wall's paper. So we have two very different plumbing graphs, and it's clear that they are not homomorphic because one of them is a homologous sphere, it has trivial H1, and the other one has H1 with 17 elements. So actually, the one is covering of the other with the covering group Z17. And if you look at the Q series, so we compute them on the computer, and they actually really coincide up to this prefactor. And this prefactor is related to the Casson invariant. It will be this -6 times Casson invariant. So this is the example. Okay. Yeah, and I cannot move it because this is the last slide. So thank you.